My name is Abhishek Shetty, and I work as the lead scientist in the rheology group at Anton, Paar, USA. I'm pretty excited to be here today, and the focus of my discussion for the next 45 to 50 minutes or so is going to be on advanced material characterization using a dual motor concept, and it's called a multi-drive system. And I'll show you in the coming slides as you can use it as a full-fledged rheometer and a dynamic mechanical analyzer. And I would like to thank everyone who was able to join today, who could spare some time from their schedules to join this webinar. I will hope to make it pretty interesting. A quick outline before we begin today. The talk will first start with the unique design concept, where I'll spend some time talking about different types of modes which the device can do, and we'll go through all this: combined motor transducer, separate motor transducer, linear drive for DMA type measurements, and then also some unique things where you can combine axial and torsional type modes to do some unique experimentation, which is traditionally not possible with other devices. And typically, to do measurements, which I'm going to talk about today, uh, you need multiple devices, two or more. In some cases, four devices are needed for all the things I'm going to discuss today. And this is a very important topic when you're trying to do more but with less, and you're trying to reduce footprint in your lab. And this is very relevant in today's world, especially academic and high-tech lab settings where space is a premium. And benefits of having such a modular device configuration which can work in different modes will be showcased today by me in different application examples, and we'll talk about liquids, solids, powders. Now let's talk about the multi-drive device a little bit more. I mean, this center picture, what you see here, this is a traditional MCR or a modular compact rheometer, single drive rheometer system, where you see this electronically commuted EC motor in the upper chassis here. And this is what we have all known as a traditional rheometer, a controlled stress rheometer, which we are all very familiar with. And if you take a look at the mechanics of this, the electric current is actually applied to the motor, which results in buildup of a magnetic field, which basically drives the drive shaft. And then you basically calculate torque from this motor current. And this does not need any independent torque sensor, because you're calculating the torque from which all rheological parameters are calculated. And you also have an optical encoder, which from where you can calculate things like strain rate, etc., which then can be transformed to rheological properties. And this is the traditional device, control stress rheometer, where you can use different types of temperature devices and all the other accessories we talk about in our general portfolio. And to some extent it can do DMA as well, because you can do DMA in torsion, especially if you have solid rectangular fixtures or parallel plate type geometries, where you can still do some DMA type characterization using this device. Now, this multi-drive device, which I was talking to you guys about, it also comes ready with an option to put a rotational drive in the bottom chassis here. And this converts this into a separate motor transducer, or some people like to call it a strain controlled rheometer. And here you can see there are two drive units now, and these two drive units can be employed in a synchronized fashion, where the lower drive now applies the deflection, and the upper drive is actually is stationary, and it basically acts like a torque transducer. And again, the speed and the angle of deflection from the bottom motor and the torque from the top motor can then be used to calculate rheological parameters. And now you can see how one device can be used as a controlled stress rheometer and also as a controlled strain rheometer by just including this bottom motor in the bottom chassis here. Now, since you have two motors, you can also do some unique experiments where these two motors can rotate in opposite direction, and this allows one to do counter rotation type experiments, which are very, very unique to this multi-drive setup, where now you can think of these both drives oscillating in opposite directions, and then the speed or the angle is equally distributed between these two drive units. And again, you have torque and normal force data coming from the top motor, which can be used to calculate rheological properties. Now, what this does is this really opens up new capability of experimentation, and this really extends the range of conventional rheological measurements. And I'll show you several application examples throughout the talk today, where we will talk about this. Now, you can also put a linear drive. In the previous slides, I talked about a rotational drive, but now let's talk about a linear drive in the bottom chassis. And here the upper drive actually is held at a fixed position. And now you can do axial movements with the linear drive here. And this really opens up other capabilities like measurement and extension, bending and compression. Your typical DMA type experiments in the axial mode. This device also has some limited TMA capability, though I will mention that it's not a full-fledged TMA device, but it can do some thermomechanical analysis as well. And I'll show you more examples throughout the talk as well. My hope today, by the end of this talk, is to show you guys that this multi-drive device in turn can act as a universal platform, for rheology and dynamic mechanical analysis. And when I say this, it's a full-fledged device where you can do full-fledged rheology and full-fledged DMA on one device. So in the coming slides, that was a good introduction to uh, the multi-drive design concept. Now I want to go over different application examples where I want to highlight the unique capabilities and what all things can be done with a device of this sort. The first example I want to show you is a classic pressure sensitive adhesive example. Pressure sensitive adhesives are a great example for soft materials, right? When you're characterizing moduluses, which can vary from all the way up to 1 megapascal in some cases, and to several hundreds of pascals. And typically people in this industry, they do a lot of frequency sweeps. They're heavily used in the PSA industry. And here I am showing you some data uh, of a frequency sweep measurement on a PSA type. It's a double-sided tape, which was investigated with a parallel plate type geometry. Now, uh, this was done on the multi-drive device where you can see data from both the CMT and SMT mode, right, which we talked about earlier. And if you take a look at the black data, which is in the CMT mode, you will be tempted to interpret a curious power loss scaling in the data. If you look at this increase in modulus as you increase frequency. But one needs to be careful because we know that this data at high frequency is plagued with instrument inertia, which actually is not a material property and happens a lot in CMT or control stress type rheometers. Now, the advantage of having a multi-drive is you can actually investigate the same sample in SMT mode. And when you have a separate motor transducer type device, you can actually see that you don't really see this spurious increase which happens in the CMT mode. And you can extend the characterization by almost a decade in frequency. So this slide hopefully shows you, advantages having a dual motor type setup where you can do both CMT and SMT type experiments on this PSA, where at least I showed you through this frequency sweep experiments. Uh, there are different, one can do, there are different solutions one could do to increase this range if you just are stuck with the CMT mode. One can actually use larger geometries, and I'll show you, maybe it will become more clear in the next slide where when I show you some equations, how you can extend the range if you just have a CMT mode by using a larger geometry. But typically larger geometries don't really work in the PSA industry because typically, people are doing temperature sweeps and stuff in this industry where the material really becomes very stiff at the low temperatures, and you kind of need to worry about torsional compliances. And typically you go with smaller geometries. Now, if we talked about the CMT and the SMT modes earlier, and if you take a look in the CMT mode, both the torque uh, and the measurement and the deflection actually is happening on the same side of the device. And in the SMT mode, the application of deflection and the measurement are actually happening on opposite sides, right? You're driving it here and you're measuring from the top transducer. So it's a separated motor transducer type experiment. And if you take a look at the total torque, basically is a summation of the sample torque plus the acceleration torque. And typically the acceleration torque is the torque which is needed to accelerate the measuring system. And typically it has an omega square scaling. And that's why if you do some simple quick math, and if you take a ratio of the total torque to the sample torque, in the CMT mode, it scales as omega square. And this is what you see at the really, really high frequency. You see that spurious increase where your data is now affected by, instrument inertia. And that's what happens in a CMT type device. And I also said about this, if you increase the diameter of your geometry, you can see the sample torque is the total torque has an inverse dependence to the power 4 with the radius. So you can actually, one of the strategies could be to increase the radius, but at least for the example I showed you, that doesn't really work that well. So you kind of need to use the SMT mode, and which really if you look at the SMT mode, it doesn't really need this term, because your torque measurement is separated from where you're applying the deflection. So this reduces the inertial effects dramatically, and that's what you saw in the previous slide. Hopefully, I was able to show you that. Now, in order to extend the frequency range, typically what people do is they do frequency sweeps, and these are carried out at a bunch of different temperatures, and people do something called time temperature superposition to extend the frequency space. And this broadening of this usable temperature and frequency range is very useful, and it's of high interest to people, because, and you also need to worry about some challenges, right? Because at very low temperatures, the characterization of the material, because the material is very stiff, so you need to exactly compensate for the torsional compliance in the system. And at very high temperatures, or at high frequencies, you need to worry about softening of the sample at high temperatures at least. And at high frequencies, there could be inertial effects, which we saw earlier. So you need to have a controller which can control both these entities very well. And this is some data which was generated on an SMT type device, where I'm showing you frequency sweeps, which were done at a bunch of different temperatures from -80 to 170 C in 1 centigrade intervals. You can see there's a bunch of different data here. And the characterization across the entire frequency space of the rheometer, which typically rheometers have specs of 100 hertz, and you can see how you can actually characterize the materials completely till 100 hertz. This will be very difficult to do if you just have a CMT device, where typically once you start going low in modulus and at high frequencies, you see this spurious increase, which I was talking about earlier. Now you can also take this frequency sweep data and convert that into temperature sweep. So now you can see how this frequency sweep data, which I'm showing you here, can be converted into temperature sweeps at a bunch of different frequencies. And you also see, the glass transition of the PSA. So what I want to highlight here is, if you have an SMT mode which can accurately compensate for torsional compliance, it allows for precise characterization over the widest temperature and frequency ranges in a typical rheometer experiment. And this will be clear when I show you the next slide, where typically PSA performance is correlated to viscoelastic properties of this bulk adhesive. And typically the data which I showed you earlier, you can then use time temperature superposition on that data and extend and generate a master curve data, as I show you here, almost 25 decades in frequency. And this is possible because you characterize these materials to the full range to start with, right? So it all depends on how good your initial data set is. So if you have a very good data set to work with, you can extend it even more, like in this case, at least 25 decades. Um, and you can also take a look here, like you get a bunch of different glass transition temperatures as well as a function of frequency. And people skilled in the art or who work in this area can develop empirical equations which relate this frequency dependence of TG to the activation energy for the glass transition. So hopefully the PSA example is clear how you actually can do more with a multi-drive type device. Now let's move on. Now when you do non-linear characterization, which is of prime interest when you work with polymers, polymer melts, especially when they're characterized at high strains or high deformations, typically a parallel plate type configuration is used. And typically you will see that you'll frequently encounter like an instability in the flow. And here I'm showing you a video where this is what manifestation of edge fracture looks like. And this greatly affects the accuracy of your measurements because this hopefully this video shows you what's happening as you increase strains on a polymer melt. And it has been shown in literature, like Christian Friedrichs's group has done a lot of work in this area, and they have studied this instability in detail, and they found that the kinetics of this fracture front propagates inward radially. It starts outside and it propagates inward. These are some images for some work I believe they did on polystyrene melts. Now, you really want to characterize your polymers at the processing level strains, which involve higher deformations. So how can you extend measurements, right, in such a scenario? So here, again, having a multi-drive device where you can actually now put a bottom motor and convert that into a separate motor transducer type device really comes handy. And Thomas Schweizer's group at ETH Zurich, they have done a lot of work in this area, and they've published several articles on this where they developed something called a cone partition plate. And the idea here is to use the rheometer in an SMT configuration, where you see the setup actually has a cone partition plate, which is shown as symbol 1 here, which is used to stress the sample from below. So the deflection is happening from below, and the upper geometry is a stationary partition plate. So only a small sample volume below the inner plate is used for the characterization. And this has advantages, as you can see in the image on the right here. Like, even though edge fracture has happened, and as we saw earlier, the fracture propagates inwards. You can see, even though the fracture has started from in the outside periphery, the sample inside where the measurement is happening is still intact. So what this means is that now, hopefully this will be clear in the bottom data slide here, where the polystyrene data was generated on a traditional cone plate versus a cone partition plate. And you can see how for steady startup shear experiments, almost a factor 10 increase in shear rate can be achieved just by using a cone partition plate. So that's another unique thing with a multi-drive device. Now we talked about artificial, edge fracture effects. Now let's talk about another experimental challenge, right? Which is basically radial migration of the sample. Hopefully the video here convinces you how at high shear rates, the sample can actually migrate out of the gap. And typically for Newtonian materials, there are equations which can predict at what shear rate this would happen. This would typically depend on the surface tension, the density of the material, the height or the gap you're using in the system. Uh, Here I'm showing you some data this was a cosmetic cream which I characterized, and this was actually characterized in a counter rotation mode, which I talked about earlier, where two motors are employed in counter rotation fashion, and you can see that I can actually extend the characterization range by using counter rotation. If you see just the single drive or the SMT mode, I can only go up to like 6,000 inverse second, but using counter rotation, I can actually extend it to almost 2 times that. So this is unique because because of the stagnation plane which is created when you move the two motors, and if you divide the deflection like 50% equally, equal speeds if they are moving, you can create a stagnation plane, and that reduces the gap to h/2, and then you can actually extend the characterization range. And this is relevant because many flows in nature, like typically microfluidic flows or lubrication flows or your coating flows or flow through nozzles, etc. They need high shear rate characterization. And typically it's very difficult to measure on standard rheometric configurations. And hopefully I show you some data in the next slide where this becomes more clear. Uh, this is some data I generated on a polymeric solution, xanthan gum. This was measured at a bunch of different gaps, as you can see. Um, a couple of words of caution before I get into this. One needs to be very careful while doing such measurements because you kind of need to do narrow parallel plate rheometry type experiments, and you need to worry about all these artifacts which can come in the data, like especially things like viscous shear heating, edge fracture, secondary flows, etc. So you kind of need to address them, and I did that actually, where You can see we did not really see any viscous shear heating, or we did not see any drop of stress with increase of shear rate. So there was no edge fracture. We also computed some Reynolds numbers to ensure that we are below the limit of secondary flows, where secondary flows could actually affect your results. The one thing which we had to pay attention was once you start going down to very very small gaps, gap parallelism becomes a big issue, and that can actually throw the data off. So we used a formalism developed by Davies et al., which was published in Journal of Non-Newtonian Fluid Mechanics, where the idea is to do some experiments with a Newtonian oil at different gaps and figure out what is the error in gap. And then once you have that, the results of the final sample, which is then xanthan gum in the system, is corrected with that gap error. And you can see this is the more details in this paper here. And with correction of the data, I could really extend the data in excess of 100,000 inverse second. So you can clearly see the benefit of having a counter rotation type device. Another interesting example here, where this slide hopefully shows you the power of probing different modes on the same rheometer, and this is for instabilities, like especially Taylor vortices, like which actually manifest at higher shear rates when you use a Couette type geometry. Uh, and typically these Taylor vortices actually happen at a critical shear rate in a concentric cylinder system. And here you will see that the same experiments were done in Searle, where the the bob is rotating, counter rotation where both the upper and the lower geometry is moving, and then the Couette type flow where the outer cup is moving. And you can see by incorporating these three different modes on the same device, I can actually extend the characterization or understand the effect of when Taylor vortices happen. Um, and especially in the SMT mode, you don't see any Taylor vortices, but there are still some secondary flows which can happen and in this type of flow. So this again is a unique example where you can see how having a multi-drive device type setup opens up new possibilities. And hopefully I'll show you in the coming slides where we can do enhanced rheomicroscopy characterizations and also extensional rheology if I have time today. Now, when one does rheomicroscopy, now we're talking about rheo-hyphenated techniques, like where you're combining rheology with some sort of other technique where you can now take a look at how the structure is evolving in your system. And one big challenge when you do rheomicroscopy is that when you keep shearing the sample, the elements typically they go outside the field of view, and upon shearing, and they move out of the imaging plane. So you cannot really look at these structures for a long time. But using this counter rotation mode, one can actually create a stagnation plane. And hopefully you'll see these videos here, where now by creating that zero velocity field or a stagnation plane, I can actually visualize these structures for much longer. And this the Rio microscope setup is actually shown here above here, where you can now probe the structures both from the side in this video on the left and also from below. So you can probe both in the gradient direction as well as in the vorticity direction. And this is PIB and PDMS, by the way. And so all this, I mean, what I showed you is at room temperature, basically. Like you can characterize these because you can see there are no ovens or anything surrounding the unit here. So all this is done in at room temperature. Now you can actually also do large amplitude oscillatory shear type experiments to collect what is happening rheologically, and also we have access to intracycle information as well if you want to do detailed Laos analysis. And here again I'm talking about both the motors are actually oscillating in this counter oscillation type mode, where you can clearly see we can apply strains and understand how the properties are changing as you increase the strain of your oscillation at a fixed frequency. The second example is an interesting one where it shows you some capsules. Hopefully this video will play. Hmm, it's not, I think the video is not working, but hopefully like if the video would have played, this video actually shows you, capsules which actually have a payload in them. And you can actually understand really at what strains the capsules rupture, for instance. Anyways, this video is unfortunately not playing, but that's okay. Now, we have done some recent modifications to the setup where now you can actually go to higher temperatures. Remember the measurements which I talked to you earlier about, they were all at room temperature. But one can, use a convection temperature device, which is shown here, which is a CT600, and you can actually use a long distance uh, microscope objective, which can be coupled to the oven here, which is, and then through this tube, which is shown in green, which also houses this high temperature mirror, as you can see. And you can reach elevated temperatures up to 300 degrees. So now you can actually do experiments at much elevated temperatures. Hopefully this is a video which was taken in a setup like this, where this is the same PIB in PDMS type solution. So now you can see, using counter rotation really opens up where you can see this droplet here stuck in the stagnation plane. So now you can image the dynamics and relaxation of this droplet for much longer, which is generally not possible when you just do Rho microscopy on a single drive device. Now we spoke about edge fracture, radial expulsion, but there could be other artifacts which actually happen in rheology and they can affect your measurements. For instance, wall slip, which has been studied a lot in literature. There could be strain localization which could happen where you have, yielded and unyielded regions in your sample. And then you could also have shear banding which can happen in in liquids, which actually can make interpretation of data very difficult. And this what this does is it basically complicates processing and interpretation of the rheological data. And so you need other type of techniques. Rheology just by itself doesn't give you the entire picture. So hopefully the next slides will show you some other capabilities which are possible with a multi-drive device. This is some work where I was involved. This comes from Matt Helgeson's group at University of California, Santa Barbara, where two different techniques were combined with rheology, namely the particle velocimetry and also in situ Rho microscopy. So you can see both PTV and microscopy was done on the samples to help better understand what was happening and the in the systems where uh, what was investigated was this coupling between shear enhanced concentration fluctuations and the potential for non-homogeneous flows in entangled polymer solutions. If you look at this, the velocity profiles, and you also look at the microscopy images which have been overlaid, you see that for these entangled polymers, this is actually a polystyrene and DOP type system. At short times, you basically have these linear velocity fields. So there is no banding. And if you look at the microscopy image, there is no turbidity also being developed. But if you go to moderate times, what happens is you see these non-homogeneous structures, which are actually, you can actually take a look through microscopy. And you also see at the same time, there is shear banding happening. There are two different velocity profiles being formed on these samples. And then again, if you wait long times or keep shearing it for long times, these bands go away, and that's why these are transient bands. So now this is the power of combining, rheology with other techniques like particle velocimetry and microscopy, which gives you insight into the microstructural origins of, when flows get non-homogeneous. So you kind of need other techniques. So having a device which allows you to do those type of work really becomes critical. This is some more work from the same group where I talked about particle velocimetry, but here this was extended and Rio fluorescence type work was also done. And this was actually done on entangled polybutadiene solutions in DOP type systems, where this was probably the first probe, if I'm not mistaken, of in situ concentration and velocity profiles of entangled polymer solutions. So this was a very unique setup where using fluorescence microscopy, these concentration fluctuations, which I was talking to you about, were investigated in more detail. And if you take a look, these are some concentration profiles plotted as a function of distance from the bob as you are moving towards the wall. And if you take a look at small Weisenberg numbers, the concentration is pretty flat. This is some sort of the y-axis shows you it's actually a probe for concentration fluctuations, and it's pretty flat. But as you increase your Weisenberg number, what happens is you can see it moves away from this flatter sort of profile to a different type of profile where you have different concentrations. If you take a look at close to the wall versus close to the bulb. So again, have this really opens up new things, and you can understand this flow concentration coupling in these type of systems. This was again work done on the multi-drive device. This comes from Simon Rogers' group from University of Illinois Urbana-Champaign, where hybrid stress strain experiments were done for thorough understanding of yielding. And now yielding is a gradual transition, as we all know. I mean, it's not a binary transition. It is actually has a time resolved aspect to it. And as you increase deformation in a typical amplitude sweep, this is how yielding looks like when you take a look at moduli in a traditional amplitude sweep. So this novel experimental protocol, which was published in PNAS a couple of years back, shows you a very unique protocol where you're combining strain controlled oscillatory shear with stress control recovery tests. And this technique provides decomposition of this recoverable and unrecoverable strains, which allows you to understand the solid like and liquid like contribution to the yielding process. And you can have a much better sense of how you can actually characterize yielding in a time resolved manner. And this is a very unique experiment where this experiment involves what you're doing is in a typical oscillation cycle, you're stopping at different instances in an oscillation cycle and creeping to zero stress. So you need a device which can actually switch from strain to stress control seamlessly. And here again, the multi-drive device with the EC motor, the electronically commuted motor, really does a great job because it allows for this controlled stress and controlled strain type measurements on one device. And these new hybrid tests really shed light on the sequence of physical processes which actually happen during yielding. Simon's group has taken it much further, and they've done a lot of work on this. And please check him out. I mean, check out the recent articles published by the group where they have used this hybrid stress strain protocol to really uncover underlying material physics, which is traditionally not possible if you just do an amplitude sweep. Now, this is an interesting slide where what you're looking at is actually, again, a hyphenated technique, a Rheo hyphenated technique, where you're doing Rheo microscopy, but this time it's not microscopy. You're actually coupling the rheometer with the confocal microscope. And if you take a look at this rheometer, it looks like a very odd-shaped rheometer, right? Where you have all this entire space in the bottom chassis here. And typically, for such applications, we actually make a unique multi-drive where all the stuff which I talked about still holds, but what is unique about the system is the electronics, which is typically in the rear side of the rheometer, is actually separated from the device. So now this really opens up new capabilities because now you can actually butt this rheometer with a confocal microscope, or you can actually put it uh, in a glove box if you want to separate, where typically you don't want to put electronics inside a glove box. So you can actually do those type of applications are also possible. So this is again an example of a multi-drive device. And here you can see that it is integrated with an additional bottom motor for counter rotation. So this is not only Rheo confocal microscopy, but also Rheo confocal microscopy with counter rotation. So here the rotation of the second motor is via this belt, if you see, which actually is tied to the shear cell assembly here. So you actually are doing counter rotation, and Jan Vermaand's group actually developed this, and they have studied many different things actually, and this data is actually on a model depletion gel at different shear rates, and you get much better, both resolution, both temporally and spatially, which can allow you to study fast dynamics, under shear flow conditions. So this is another example where you can use a multi-drive device to do this. Now let's talk. I've talked a lot about rheology, hyphenated techniques. Now let's talk about a totally different application. And now all the stuff which I'm going to talk about in the next couple of slides is going to be with the single motor or the CMT mode. Now, you can actually convert the the CMT mode of the rheometer into a full-fledged powder rheometer to study, dynamic properties of powders. And this slide hopefully shows you the incorporation of a powder rheology accessory, which I show you here on the rheometer. And it actually has a pressure sensor and a mass flow controller, through which, and there's a bottom glass frit here through which you can send controlled amounts of air through this bottom frit. And you can do classical fluidized bed type experiments where now you can actually get pressure drop as a function of volumetric flow rate. And you can characterize your packed bed and fully fluidized, regions in your. And I show you some data for an additive manufacturing powder here. There's also a video here. Hopefully it plays. It's actually on a fluidized catalytic cracking sample, where you can understand, at what point does the material fluidize. And the other unique thing about the setup is, since this is actually coupled to an air bearing rheometer, and you also have a spindle, right, to which is connected to the top head of the rheometer. You can actually also understand, or study the evolution of torque as a function of flow rate, and you can understand at what point does the material completely fluidize. And coupling it to an air bearing rheometer really helps to characterize very, very low torques. And if you typically look at most powder devices which people use in the industry, they are mostly mechanical bearing devices. So having a powder rheometer, which is actually on an air bearing device, really opens up new experimentation when it comes to characterizing materials at really low torques, which is very important when you do fluidization type experiments. Um, and also, you can see this dust protection hood here, which you have a completely sealed system here, and this allows characterization of hazardous powders. Since it's completely sealed, you can actually put it in a dust protect in a glove box or a hood, and study hazardous powders as well. No, this is some study where I was involved. This was a collaboration with Christine Henria's group, and this got published in Chemical Engineering Science a couple of years back, where defluidization experiments were done on mildly cohesive materials. And one of the aim of this work was to show system size independence. We wanted to show that experiments which are done on traditional fluidized beds can be scaled down to the scale of a rheometer. And if you monitor literature in this area, where people have talked about how defluidization can be identified as a bulk measurement to extract interparticle cohesion between particles, using some sort of a modeling approach. And what this work paved the way was, since we can actually scale the system down to the scale of a rheometer, this also means that this work really opens up the feasibility to couple with smaller scale DEM simulations, because now you can actually try to simulate what's happening on the scale of a rheometer. And having uh, a stirrer here also means that if materials which actually channel when you do fluidization uh, can be fluidized, because now you can actually add some energy through the stirrer to help fluidize these systems. And more details in the paper below. And I don't have time to, we have done a lot more work actually. I just wanted to mention one thing quickly here. A very interesting application where I was involved with in recently was studying, real gas pyroclast mixtures at dynamic conditions, at the real scale concentrations, like which happens with pumice-rich pyroclastic density currents when a volcanic eruption happens. And we all know that it's one of the most lethal volcanic hazards, right? These pyroclastic density currents. So we actually, for the first time, used the powder rheometer to study these things, and it was a very interesting paper. If you more details here, actually, this is just hot off the press. It actually got published in Nature Communications recently. So again, what I wanted to show you is the scale of things you can do on a multi-drive device. Hopefully, I've given you a lot of examples, and more are coming. This is some work which comes from Anson Mars group at Connecticut. Binder jet printing has gained a lot of traction, and this is very popular, especially with pharma type applications, because this is all done at room temperature. So, and additive manufacturing, we have been talking about that a lot. where it's a layer by layer building of structures. But binder jet printing, where you do this, but you don't need elevated temperature and stuff. So this means, like, most of the heat sensitive stuff can be easily, like heat sensitive active pharma agents, for example, can be easily incorporated into this. Now, turns out, characterization, because most of these are powders to start with, before these tablets are made, or 3D printed tablets, the powder characterization is very key. And when people are trying to, explore new pharmaceutical excipient type combinations that can be used effectively in this binder jet printing process, you need like some sort of dynamic and quasi-static characterization. And this is what was actually done, and more details in this, where, these flowability indices and cohesion was measured using a powder rheometry setup. More details in this, in this paper below here. Now, one thing which actually affects powder properties a lot, powder flowability depends on a lot of different parameters. The both intrinsic to the powder, which are things like, particle size distribution, all these things are intrinsic to the powder. But there are these extrinsic factors which also are very important when you're trying to understand flowability of powders, especially, temperature, effect of temperature and humidity. And this is actually, this slide hopefully shows you the incorporation of a ring shear cell to understand quasi-static properties of powders on a single drive rheometer. Here, you can actually put your powder, and then there's a convection oven where you can actually now apply different temperatures and even humidity conditions. And typically, there are no devices out there which can characterize such things. So this is very unique. It opens up really new experimentation. This example which I show you here is actually for a vitamin C type, a drink, which you actually take the sachet, put it in water, dissolve it. So we wanted to understand how humidity affects flowability of this powder. Uh, and the image here, I don't have details to go over, more Coulomb type diagrams and stuff, but hopefully I'll show you that, what is happening is, as you increase humidity, all these parameters which you get from a more Coulomb type analysis, they actually increase, like your cohesion, the unconfined yield strength, they all are humidity dependent. So when people are designing processes where they are, putting these powders in a sachet, you need to understand the effects of extrinsic factors. So, having a device which can allow you to do that becomes very important. And hopefully this example clearly shows you effect of extrinsic factors. Here especially, I talked about ambient moisture, but we have done a lot of studies where, we have studied temperature effects on polyamide, powders which are used for in additive manufacturing. So again, very unique experimentation is possible. And clearly, these extrinsic factors actually have a huge impact on flowability, which drives a lot of the processing of these powders. Now, let's talk about the last part of the discussion today. And we talked about general rheology, Rheo-hyphenated techniques, powder rheology. But now let's switch gears and talk about what you can do in terms of DMA capability, right? So we talked about two rotational drives or a single rotational drive in the top chassis for all the discussions we had earlier today. But what if you put a linear drive uh, in the bottom chassis? And this again opens up new experimentation. Like, now you can actually characterize your materials in the axial direction, right? So things like bending, compression, uh, all the measurements which typically you do on a DMA type device, like 3-point bending, cantilever, all those are now possible when you put a linear drive. And one thing to point out here is the stroke length or the displacement possible with a device like this is almost 9,000 microns. Now, there are a lot of, I've seen examples of traditional rheometers which claim that they can do some sort of axial DMA, but the challenge is most times the specs on those systems are, they can do about 50 to 100 microns in axial displacements. So this is a huge improvement in that regard, where you can do 9,000 microns, and this is actually a full-fledged DMA. And this becomes more clear when you try to characterize, films and stuff in an entire temperature range, where for the same force you need higher displacements as the material traverses through the glass transition. Now, for the bulk remainder of my talk, I'm not going to talk about, conventional DMA type examples, which any device can do. What I want to point out in the next remaining minutes is some unique things or highlight some unique capabilities in terms of experimentation, which actually is possible with this combined axial torsional type setup. Now, you might be wondering, what do I mean by this combined axial torsional DMA? So let me first explain what I mean by axial torsional DMA here. What I mean by this is that you're using two different actuators. Uh, you can see one actuator is actually the rotational drive, which we have spoken a lot about today, and then which allows you to do measurements in torsion, where you're shearing the sample. So you get something called a G star or the shear modulus. And then you have another actuator which applies axial deformations. It could be as in static or dynamic conditions. And if you do it in dynamic conditions or in an oscillatory type flow in the axial mode, you basically get an extensional type measurement. So you can get both G and E uh, type data on your samples. Uh, and now you can actually get this data on the same sample, on the same specimen in a single measurement under the same environmental conditions. Now, if you take a look at a critical review paper which was written by Shogel, I think back in the early 2000s, I'm talking about the Poisson ratio determination here. This is the unique application I'm talking about, where one of the things mentioned in that critical review paper was, need of a device which can actually do measurements on the same sample in the same environmental conditions so that the boundary conditions, everything are same. So the Shogel dreamt of a device where this could, if even it was possible to do such measurements. And now in turn to in recently we have developed this now where you can actually do this measurement where you can set up a multitask experiment where you can now measure G and E at the same temperature on the same sample without changing it. And for isotropic samples, you can then use this E and G, at least for an isotropic sample in a infinitesimally small strain limit. Poisson ratio can be defined as shown here. And hopefully I'll show you more data here. Like, so based on that G and E measurement using the combined axial torsional mode, right? You can now study this as a function of temperature within a single test protocol. And this was not really possible before. And you see the evolution of both moduluses here below the glass transition and above the glass transition. And what you see here is not only effect of temperature, but you can actually study effect of frequency as well. What happens, and you'll see soon in the next slide. One thing I forgot to mention earlier, for these type of measurements, it's highly recommended that you use cylindrical fixtures because the stresses are more uniform, and there are more review papers which talk about why cylindrical fixtures are preferred over rectangular fixtures because you have these warping torsion type effects with rectangular fixtures. So we used cylindrical fixtures for this work, and this shows the complex dependence of Poisson ratio on frequency and temperature. And and for the most part, people assume Poisson ratio to be a constant because the literature data on Poisson ratio is scarce to begin with. Now we use this to the formalism which I was talking to you about, the combined axial torsional, we extended this to multiple different polymer types. Like we studied amorphous, semi-crystalline, thermoplastic type materials, um, and we characterized the Poisson ratio as a function of temperature. And more details actually are in this paper, which was published in 2023 in the Journal of Rheology, which also it also ended up as a cover article in the front page of JOR. So you can see it's not really a constant, but it really changes with temperature. So having a combined axial torsional uh, type device really opens up new experimentation uh, for folks, and this could have significant implications, right? For especially people who work in the simulation groups and who are doing FEM or finite element type simulations and modeling. Most times they need data on Poisson ratio to model systems, and typically there is no data, as I said earlier, or it's very scarce data is available. So really measuring it really helps in that case. Now, the approach of Poisson ratio, which I talked about earlier, like those equations, they're only valid for, isotropic materials. But what about anisotropic materials, right? Because in reality, we work with so many different types of materials, and anisotropy is a huge component of that. Can this combined axial torsional, multi-step protocol, which I've been talking about, can it help us here, right? That's so here I'm showing you some results using the same protocol for a polyketone and a carbon fiber reinforced polyketone. And if you see, the open symbols are for the reinforced entity, and the closed symbols are for just the polymer polyketone. And if you see, take a look here, the fibers really result in an increase of both G star, which is the shear modulus measured using the rotational drive, and E star, which is measured with the axial drive. And you can see a factor of 6 to 12 difference. Actually, the G star actually varies almost by a factor of 6. And typically, if you take a look at typical polymers, typically the ratio is between 2 and 3. That's a typical range for polymers. But if you have anisotropy, that's when these become much higher than 2 to 3, which we canonically know for normal polymers. So again, now you have a way to measure this ENG. And also one thing you would notice here is ENG. The ratio of ENG is highly temperature dependent. And if I plot this ratio of ENG as a function of temperature for a pure polymer like polyketone, you can see it's between 2 and 3, and it has a slight frequency dependence, but uh, nothing out of the ordinary here. But if you take a look at this carbon fiber reinforced polyketone, you can see it varies almost right from 3 to 6 times, and it is temperature dependent. So again, now we see that how you can characterize anisotropic materials with a device like this. Now let's take it a step further. Now, one could compute, like, you're measuring these loss factors in shear and in torsion, right? So both, because you're doing oscillations both in rotation and also in the axial mode, you basically get loss factors, and one can compute something called zeta, which I show here, which is the ratio of the loss factors measured in torsion to the ratio of loss factors measured in extension. And uh, the data in the center is for a thermoplastic urethane sample as a function of temperature and frequency. And you see this 3D plot here where nothing really interesting is happening, where you see that the tan delta in both the modes are sort of independent of the deformation mode. So, if you take on a whole, the ratio is close to 1 within the experimental uncertainties. But the second plot, which is the glass fiber reinforced plastic, which we know is an anisotropic material, it's actually very interesting. If you take a look at this, first of all, take a look at uh, the loss factors both in torsion and extension, and they are completely different. They're not they don't cater to what an isotropic material looks like, where you see a maximum, which definitely is interpreted as the glass transition. Uh, they actually happen at the same temperatures, both in torsion and extension, but it's the relative intensities of this maxima which actually differ than the TPU case, right? And this is due to the anisotropy present in the system, and you're probing different internal frictions, which is the interaction between your polymer and the matrix and the glass fibers. The interaction actually is different it depends on the kind of mode you're actually using as the deformation. So now you can see, and if you plot the same zeta, which I showed you earlier for TPU, it looks totally different. It doesn't, it deviates strongly from 1, as you can see. It's much lower in this case. So it clearly shows you, that, you can actually characterize anisotropic materials. And can this zeta be used as a, dynamic fingerprint of an anisotropic material? So let's go back to our polyketone example, which I talked to you earlier about. And you can see when I use the zeta factor in this case, a factor of almost close to 1 is obtained, at least for data above the glass transition for the pure polymer polyketone case. But when I use the carbon fiber reinforced polyketone, you can clearly see the data both below and above the glass transition deviates. The zeta deviates from 1, which clearly shows the anisotropy present in the material. So again, this is these are the unique things which one can do with a combined axial torsional type device, and you can also see it also has a frequency dependence. So now you can actually study all this in a single experiment. So this really reduces the time of characterization needed, and you can actually distinguish anisotropic structures and understand the dependency on temperature and frequency using these unique type of experiments which I talked about. I think I spoke a lot today. Hopefully, I've showed you how a multi-drive instrument, can serve as a universal platform for mechanical testing, right? We talked about CMT modes, SMT modes. It can be used in the DMA mode. It can be used for powder rheology. We talked about some unique experiments which are possible with these combined axial torsional type devices. In the SMT mode, we talked about the cone partition plate, extension of shear rates, counter rotation for microscopy, Rio hyphenated techniques. We talked about DMA through Poisson ratio, combined axial torsional type experiments for Poisson ratio determination, and also, anisotropic material characterization. I think I've tried to cover a lot because I wanted to show you the breadth of things which are possible by having a device of this sort. So with that, I think I will stop here and open the floor for questions. And thank you for listening to me today.
Thank you, Abhishek. Let's take some questions from the chat window. Our first question, can the instrument be combined with other spectroscopic techniques?
Yes, I mean, I didn't have time to go over that, but yes, we can combine it with other. In fact, we actually have a ready-made solution for with Raman spectroscopy, for instance, because we have another product line, the Cora series of the spectrophotometers, where we can integrate a Raman and a rheometer, and you can do Rio Raman actually. This could be very interesting for a lot of different applications. So the answer is yes, and we can also couple some other techniques where we do a lot of customized projects as well. So yeah, we can definitely do that.
Okay, next. What type of powder characterization is possible on this multi-drive device?
I know, like I try to cover a lot today, but you can think of all different types of characterization. Like, we can probably do dynamic characterization. We can do quasi-static characterization. Those are the ring shear cells I talked about. I didn't have time to talk about dynamic testing, where that's an entire slew of experimentation where you can actually understand effect of dynamic conditions on powder flowability. And this really happens in real life when you're trying to convey a powder, or it's actually getting uh, moved from a conveyor to a hopper maybe, or there are several touch points. So understanding both quasi-static and dynamic conditions are possible, and over the top of it we can understand the effect of extrinsic factors like temperature, humidity. I've worked on very interesting projects where things like sticky point can be determined using the humidity setup. So we actually can understand, at what point does the powder become really sticky. So we can do these type of experiments on this device because it's a full-fledged powder rheometer also.
Okay, next question. DMA in immersion, is that possible?
DMA and immersion, yes, we do have capability to do DMA and immersion as well, where uh, most of the DMA geometries like parallel plating compression or cantilever or three-point bend, we do have capabilities where you can understand effect of other fluids and stuff on your materials. Like these could be seals, or maybe it's in an oil or something. Yeah, we do have capability to do that as well. Yeah, we do DMA and immersion too.
Okay, next question. How high in temp can the DMA device handle in axial mode?
I think the stuff which I showed you today, those are mostly with the CTD 600. That goes up to 600 degrees, but we do have capability to go much higher. Like we have a multi-drive device which actually goes up to 1000 degrees. So you can do axial measurements like a three-point bend type measurements up to like 950 to 980 degrees as well. So 1000 degrees, I would say close to 1000 degrees is also possible with DMA axial type measurements.
Okay. Can the device you mentioned be used for curing experiments?
Yes, I mean, so if you remember the first part of the talk where I was talking about traditional rheology, right? That the single drive system where you just have the top motor here, as is shown here. Yeah, this can be used for curing type experiments. And the fun part is actually, I was talking to a customer not so long back, where they wanted to do curing, and once the substance is cured, they also wanted to measure it in compression. So having a multi-drive device is really unique because you can not only characterize the curing part, and once the substance cures, and you can put the axial drive inside, and now you can actually characterize the same material in the DMA compression mode as well. So you can do a lot more, a lot of things with the device. So yeah, you can definitely do curing type experiments as well.
Okay. When using the microscope feature, would it be possible to see 1 micron domains in a compounded material?
1 micron, I mean, that is the resolution, I would say. Like, yeah, that is typically the wavelength of light, right? Like on the scale of 1 micron. So, I mean, as long as you have, structures more than, 1 micron or 2 micron, I mean, you can kind of see it, but it also depends a lot on the sample as well, right? If it's very turbid, I mean, we have measured crude oil type samples as well at very small gaps. So it's all depends on the sample too. But I mean, typically size scales above 1 micron, I would say, like, at least, that's a good starting point. We can at least take a look because that is within the resolution of the wavelength of light.
Okay, next question. Can you comment on extensional rheology measurements possible with the device for liquids?
Yeah, I know, like, I didn't have time to talk about that today, but we do have capability where you can think of, this setup here where I can have two parallel plates and actually I can put a liquid sample there and I can do these step strain type experiments where one can understand, capillary breakup or filament breakup, if I can call it. And one can then couple this setup with a camera. And you can take images and analyze those images and understand how the filament diameter is thinning, and then you can actually fit an exponential profile to those the thinning of those filaments and basically get something like a relaxation time. So you can do some breakup filament type experiments as well with this device, and um, that is possible. Yes. Uh, Firstly, I would thank everyone for staying back and listening. What I want to end is, like, I just showed you some examples here. These are the things we have worked on, but you guys are material experts out there in industry or in academia. I mean, the avenues of experimentation are immense. I mean, you can do a lot with this device, and I'll really hope to see new applications being developed on this setup because you can do a lot. I mean, that's where I'll end. It's a multi-purpose device where multiple things can be done and equally well. I mean, that's the important thing. Like, you can do each of these things very, very well with a device like this because it has state of the art specs when it comes to rheology, DMA, or even a powder rheometer. You take it actually does a great job in all these different fields. So with that, I'll stop and thank everyone for attending again.